It's telling her everything that's happening in the school for the next 6 weeks. So sort of here's what's going on. Sort of maybe a little on the fast side and a little bit short. What I want to do is cover the derivatives of exponential functions that have bases other than the Euler number. And then I want to go over the derivative of sine and cosine.
Okay.
And so we're going to do a couple of examples of these and a couple of examples of sine and cosine. And the reason is I have badminton like tomorrow and Thursday.
Okay.
And so that'll be, we won't have a lesson tomorrow or Thursday. Friday, we'll do the review. And then on Monday, we'll have our last calculus test, which is like 4 lessons.
Yeah, sounds good. Yeah, really.
Yeah. What's that?
Yeah, no, it's pretty, pretty quick.
It's nice. We're lifting along quite nicely.
Mm-hmm.
Okay. So anyways, the derivative of an exponential function, what kind of function is the derivative of an exponential function? Is it like, it's a, let the record indicate that Lindsay is making the exponential function sign. Correct. Okay. This is going to be another exponential function. We just have to figure out what we need to do to make it work. Oh, look at that. I can make that level, sort of. Okay. So what I want to do is I want to make this into sort of not an exponential function. And so I'm going to take the natural log of both sides. So sorry, this is kind of a proof. This is kind of a proof that involves a little bit of implicit differentiation again, which is what I'd done before. Okay. The log of something with an exponent, using our log rules, the exponent can be written in front. Okay, so the natural log of y is equal to x times the natural log of 2. So this is the base of the original function. The natural log of 2 is just a number, just like every other number. Now I'm going to take the derivative of both sides. The derivative of the natural log function is 1 over whatever the argument is. And so on this side, we have 1 over y. But remember, y is a function of x. And so we have to remember that to use the chain rule. So this is our y primed here. Okay, the derivative of the inside of the function. And the derivative of x is just 1. 1 times the natural log of 2 is the natural log of 2. Okay, so we want to get this exclusively in terms of y primed. And so y primed is equal to multiplying through by y times the natural log of 2. But y is just 2 to the exponent x. And so y primed is equal to the natural log of 2 times 2 to the exponent x. Okay. Now, rather than go through the whole song and dance, what do you think the derivative of y equals 3 to the exponent x is?
Well, thinking it might be, how do you pronounce ln?
I don't know. A lot of people call it ln. I've been calling it ln because it sounds so easygoing.
Maybe ln 3 times 3 to the x?
It is log 3 times 3 to the x. That's exactly right. Okay, so that's the pattern. Just basically the original exponential function times the natural log of whatever the base was.
Okay.
That's it. So that's the derivative of an exponential function to any other base. So just in general.
Perfect, okay.
So if y is equal to a to the exponent x, y primed is equal to the log of a times a to the exponent x. And so You will also notice, like if you type in log on the internet, like I mean to use a calculator or whatever, the internet automatically assumes you're using the natural log rather than log base 10.
Oh, okay.
So back when I was in high school, I think it was the last vestiges of the use of the slide rule. And the slide rule took advantage of sort of logs base 10. And so, you know, we were learning how to use, well, you know, the old holdout teachers were like, oh yeah, you're going to have to learn how to use the slide rule maybe, you know, when civilization ends and you don't have a calculator anymore. Anyways, natural log is more related to natural processes, and it's a very interesting function just because it's related to the Euler base E. And the way that's a function that is its own derivative means that it reiterates itself throughout calculus quite well. Okay, so let's do a couple of examples where we have exponential functions with bases other than E. And then I'm going to jump right into the derivative of sine and cos. All right, what do I have here? Oh, well, that's no good. We've already made one of my examples redundant. There we go. Okay. What rule do we need for this one?
The one where you bring it out. I can't remember the name of it. It's a late night.
The chain rule.
Yes.
Let the record indicate that Lindsay was also making the chain rule gesture. Yeah, that's right. Okay. So this looks like y equals 5 to the exponent u. And u, oops. So y primed is going to be the natural log of 5 times 5 to the exponent u. U is 2x plus 2. And so u primed is just 2. And so y primed is going to be the natural log of 5 times 5 to the exponent u times 2. And if I substitute my u back in, I better tidy that up. So 2 natural log 5 times 5 to the exponent 2x plus 2. Okay, so yes, using the as it's symbolized chain rule where the other function comes down in front. So it's really pretty simple when we get taking these logarithms. And hopefully by now you're getting to that point where the chain rules, you know, you're fairly comfortable with using the chain rule. Okay, so let's do 3 to the exponent x squared. We're all good. We can erase this. Okay, so this is y equals 3 to the exponent u. So y primed is going to be natural log of 3 times 3 to the exponent u. U in this case is x squared. And so u primed is 2x. And so y primed is the natural log of 3 times 3 to the exponent u times u primed, 2 to the exponent x. So y primed is equal to 2x, natural log of 3 times 3 to the exponent x squared. That's it.
So do you just take the derivative of the u, put it out front, and make that the natural? Okay, I got it. Okay. Yep.
Yep. Yeah.
Throw that in there and then multiply it by the original function. Okay.
Yep. So yeah, there we go. Yeah.
Yeah.
Yep, so it's a fairly easy pattern. Once again, just the chain rule all over again.
Sounds good.
Okay. So let's do the derivative of y equals sine x. And so I don't think I put it into the preamble, or maybe I did, I'm not sure. But basically, we need to know about three things. We need to know two new things. And we need to know, we need to remember something from advanced functions, and that is the sum of two angles formula. So the angle sum formula for sine. We also need to know a couple of limits. And so I'm just going to say what they are right now. First of all, the limit as h approaches 0 of the sine of h divided by h. Okay, and so you usually get people putting in smaller and smaller values of h into this expression. We can't actually make h equal to 0 because the expression explodes and disappears on us. But we can take the limit, and this actually converges on 1. Now there's a second limit of cosine of h over h. Once again, we can put zeros in, but this explodes if we do that, but we can put increasingly small values of h in, and this actually converges on 0. The last thing we need to know for this proof is the angle sum formula. And of course, this is something that we might remember from advanced functions. This is equal to the sine of x times the cosine of h plus the sine of h times the cosine of x. There we go. Did I get that right? I think I did. Okay, so that's the sine of the sum of two values, and this is the formula that is equivalent to that. These are the three things that we're going to need to know to come up with the derivative of sine. Okay, which, by the way, I think we already know. Do you remember what the derivative of sine is, Jeff?
I think is it cos or is it negative cos?
It's actually cosine, yeah.
It's
And
cos?
the derivative of cosine is negative sine.
Yeah.
It's
Oh,
kinda-
there. Yeah.
Yeah. When you actually look at the curve and you say, well,
Yeah.
the slope right here is 0 and the slope here is 1, you can actually see that, yes, they are closely related to each other. Okay. I'll leave this here for now. I hope I don't run out of too much real estate. So let's take the derivative of sine x. And of course, if we go way back to the good old days of the difference quotient, that's equal to the limit as h goes to 0, the sine of x plus h minus the sine of x all over h. So there we go. Difference quotient all over again. Look, everybody, sine of x plus h. I already know what that is. I've carefully written it out down here. So this is sine x times cosine of h plus sine h times cosine of x. I better put a bracket around there. Oh my goodness, I've run out of real estate. Jeff, can you see that edge of the board?
Yep.
Okay. And then minus sine x, and I better put this whole thing over h. Okay. Goodbye, some formula or other. Okay. I hate to be nerdy about equal signs, but I do like it when they line up. And so I will compensate by drawing this arrow out randomly into the middle of the board and pretend that's like having my equal signs line up. Okay. So I'm just going to rearrange this with the goal in mind that I want to factor out my sine x. So my limit still stays out here. And I'm going to move the sine x over here beside its cousin, sine x times cos of h. And this whole deal is over h. Okay. And of course, it's pretty abstract. It's hard to tell where everything's going here. Uh-oh. There are two things. I realize I actually told you the wrong value for that limit. That's okay. And I had to erase that h. Lindsay just sighed. I think she just sighed. I'm not sure. So that limit was actually cos of h minus 1 over h. Okay. We're almost there, everybody. I'm going to break this up into two fractions, and I'm going to apply the limit that I got right the first time, as well as the limit that I accidentally told you that wasn't true. Okay. So sine of x times cosine of h minus 1. And I'm just going to put this over h, and I'm going to go sine of h over h times cosine of x. And if I told you this correctly in the first place, which I did not, what is the value of this? Cos h minus 1 over h is, let the record indicate Lindsay's giving the 0, either that or the OK sign. So this part disappears. This turns into 0. And the limit as h goes to 0 of sine h over h turns into a 1.
All right.
And then I'm just left with the cosine of x. Okay, so this turns into 0. I can put in my limit. This turns into a 1. And I'm left with the cosine of x.
Works.
Yeah. All right. Oh, I'm just erasing stuff willy-nilly here. So sorry, I wrote that cosine h minus 1 over h limit incorrectly. I should have known, because cosine of something close to 0 is pretty darn close to 1. Okay, let's do a couple of examples. I'm just going to quickly write down just the fact that the derivative of cosine is negative sine. What we'll do on Friday is, for a review, we'll actually look at some applications, and we'll maybe just show why that is negative sine.
Right.
Okay. So let's do the derivative with respect to x of the sine of x squared. Okay. You probably already know where this is going. Which rule should we use?
Thinking the chain rule.
Yeah, let's use the chain rule. Okay. Do I need to write down the inside and the outside, or can I just?
Nah.
I'm just going to do
I
this.
think that kind of confuses me more now.
I'm actually glad to hear you say that.
Yeah.
Okay, so the derivative of the outside function. So the sine turns into a cos, and we leave all the inside stuff alone, multiplied by the derivative of the inside function, 2x. And so the derivative of the sine of x squared is 2x times cosine of x squared. Okay. That's it. Good so far?
Yeah. That's
All right.
cool.
Okay. Here's the one that sometimes gets people. The derivative of sine squared of x. So this is where people get mixed up about where the exponent goes and what it means. Once again, it's a little bit different, but we still use the chain rule on this one. This time, the outside function is actually the squaring function, okay? Because we could write sine squared x is the same thing as, I'll put it up here, sine of x squared, okay?
Okay.
So our outside function is the squaring function, and our inside function is the sine function. Okay, here we go. So I'm going to use my power rule. So 2 sine x, there's the derivative of the outside. And now the derivative of what is the inside function here, the derivative of sine x, cos x. And does anybody recognize this from advanced functions?
Yes, I don't know what it is.
Yeah, so this is,
Wow.
it's actually a close cousin of the sum of angles formula we just looked at. This is the sine of 2x is the derivative.
Mhm.
Okay, that's that. So that's derivatives of exponential functions with other bases, the derivative of sine, and the derivative of cos. And so the next 2 days, we're just going to do sort of simple derivatives of those things.
Okay.
Friday, for the review for the test on Monday, we'll do some applications on Friday,
Right.
finding the extrema, and test on Monday, and then like it's all over. The course is reborn in at Easter.
Nice.
All right, good.
So
Okay.
what sorts of questions should we expect for Monday then?
So literally, like, it should be pretty simple. So it's going to be the derivative of base e exponential function. Even though it's not technically on the course, I'm probably going to ask a simple, derivative of ln, the natural log of something.
Okay.
Okay, and that could be the natural log of something that's got a function on the inside.
Mm-hmm.
Okay. Derivative of exponential function of any base.
Okay.
And that can include a chain rule. Derivative of a trig function. Okay. Oh, I'm going to ask you for that derivative of sine proof. That'll be question 2.
Okay.
And I expect you to get cos of h minus 1 over h. The limit as h goes to 0. That is 0.
Yep.
Okay. And there will be an application question. And so it'll be a question like, what is the maximum of, where's the tangent horizontal to sine x squared? And that's the kind of problem that we're going to do on Friday. Friday, we're treating it like a review because we're just going to be using the functions over and over again, but we'll be doing a couple of applications. So I think Friday we'll do like a 3-question lesson.
Okay.
And it will also be fairly short, but it'll just review all the rules and go over the applications. Okay? All right. Good. So Friday, I'm doing badminton tomorrow and the next day. And so Friday, we'll just do a review.
Sounds good.
Okay. I'll put up some pictures of the questions I want you to do for the next couple days.
Okay, sounds good.
Okay, great.
All right, thank you.
Thanks, Jeff.